This changes everything. For the first time in human history, astronomers have witnessed the birth of an actual planet, forming live in real time. The James Webb Space Telescope has captured an unprecedented and awe-inspiring view of a young world emerging from cosmic dust, a sight humanity has never witnessed before. Located 450 light-years away in the HH30 system, this discovery could completely revolutionize everything we thought we knew about how planets are born. This isn't just a theory anymore, this is happening right now, and scientists are in shock. A glimpse into planet formation like never before. Most planetary nurseries are hidden behind thick clouds of gas and dust, making it nearly impossible to observe the intricate details of planet formation. But HH30 is a game changer. Thanks to its unique edge-on orientation, astronomers are granted a direct, unobstructed view into its protoplanetary disk, the swirling region where brand new worlds are being sculpted from dust and gas. Why is this so significant? Well, most disks are seen from an angle, which makes it difficult to truly understand what's happening deep within them. But HH30 gives us an unobstructed cross-section of the disk, allowing scientists to analyze its formation processes with a level of precision and detail never before possible. Webb's latest stunning images have revealed a striking dark band of dust, a clear sign that planetary formation is already underway. This dust is absorbing starlight, indicating that denser material is accumulating, a crucial step in the birth of planets. Even more astonishing is that the disk seems to be flattening over time. The flattening process, a key to understanding planet formation. You might be wondering, why is the flattening of this disk so important? Early in a star system's life, dust and gas are distributed in a chaotic, turbulent manner. Particles are flying around in all directions, making it nearly impossible to form structured planets. However, as these particles collide and begin to stick together, the disk slowly starts to flatten out into a more organized, structured plane. This is exactly what Webb has observed in HH30, and it's a crucial step in planet formation. This is the same process that led to the formation of our own solar system billions of years ago. To think we're seeing this happen right before our eyes in real time is nothing short of mind-blowing. But wait, there's more. Webb has also detected high-speed jets erupting from the poles of HH30. These narrow streams of charged particles are blasting out into space at incredible velocities. Why do these jets matter? So, why are these high-energy jets so important? Well, these jets do more than just make the system look dramatic, they actually play a vital role in regulating the growth of the central star and influence how dust settles in the surrounding disk. These jets might even determine which regions of the disk have enough material to eventually form planets. Could these jets be helping to shape the future planetary system of HH30? Scientists are hard at work trying to understand that. One thing is absolutely clear, this system is alive with activity, and we're witnessing the earliest, most dynamic stages of planet formation in real time. It's a cosmic ballet in motion, and we have front row seats. How does dust evolve into a planet? Now, let's address a fascinating question: how does something as small as cosmic dust transform into an entire planet? Planet formation begins with microscopic dust grains, tiny particles floating in the protoplanetary disk. But these grains don't just randomly clump together. There are very specific conditions that must be met for them to stick together and grow into something more substantial. Thanks to Webb's powerful infrared capabilities, we've gotten a glimpse into these conditions. The denser regions of HH30's disk appear cooler than scientists had expected. This is incredibly important because cooler dust grains have a much easier time sticking together. Why? In hotter regions, dust particles move too quickly, and their collisions are too violent for them to merge. But in cooler regions, the particles move more slowly, increasing the chances that they'll stick together rather than shatter. These dust grains slowly form into pebbles, then into rocks, and eventually into massive planetesimiles, the building blocks of planets. But here's the catch: not all dust survives long enough to form planets. If particles get too close to the central star, they can be pulled in and vaporized before they even have a chance to grow into anything substantial. Dust traps, the key to planetary formation. So, how do planets actually manage to form in such a chaotic environment? Webb's data suggests that certain regions in the HH30 system are acting as dust traps, where particles accumulate instead of being lost to the star. These dust traps could hold the key to understanding why some systems successfully form planets, while others don't. Could HH30's dust traps be the early blueprint of a brand new planetary system? That's exactly what scientists are hoping to figure out. Could HH30 hold the ingredients for life? Here's where things get really exciting. The James Webb Space Telescope has detected organic molecules within HH30's protoplanetary disk. Why is this so significant? Because organic molecules are the fundamental building blocks of life. These are the very same types of compounds that were present in our own solar system before Earth even existed. Webb has identified molecules like methane, CH4, a crucial component in prebiotic chemistry, and carbon-based compounds, which are key ingredients for amino acids, the building blocks of life as we know it. But here's the real question: does this mean HH30 could one day host life? We don't know that for sure, but finding organic molecules in the disk certainly suggests that the chemistry necessary for life might be widespread across the universe. If HH30's organic molecules survive the planet formation process, they could seed future planets with the building blocks of life. This strengthens the idea that life's chemistry could be universal, not just unique to Earth. HH30 in context: how does it compare to other systems? To understand the significance of HH30, let's put it into context. There are two other well-known planetary nurseries we can compare it to, HL Tau and PDS-70. HL Tau is a slightly older system where rings of dust and gaps carved by forming planets are already visible. PDS-70, on the other hand, has actually imaged two protoplanets directly within its disk, indicating that planet formation is already well underway. Could HH30 be in the early stages of evolving into something like HL Tau or PDS-70? Or is this system on an entirely different trajectory? Time will tell, but it's thrilling to think that HH30 might one day show us what our own solar system looked like billions of years ago. Could HH30's planets become habitable? One of the most exciting questions scientists are grappling with is whether the planets forming in HH30 could one day become habitable. The central star plays a huge role in this. HH30 is a young, low-mass star, still in its early developmental stages. Right now, it's surrounded by a thick disk of gas and dust, but over time, the system will clear out, leaving behind whatever planets successfully form. However, young stars like HH30 tend to be extremely active, emitting intense radiation and powerful stellar winds that could strip away the atmospheres of forming planets. If a planet forms in the Goldilocks zone far enough from the star to avoid extreme radiation, but close enough to retain heat, it could have a better chance of developing an atmosphere suitable for life. The importance of water for a planet to be considered potentially habitable: it must have access to liquid water at some point in its development. In our solar system, Earth formed in the habitable zone, the sweet spot where temperatures allowed liquid water to exist. If HH30's disk contains enough water-rich material, icy asteroids and comets could deliver water to the forming planets, much like they did on Earth. The ingredients for life beyond water, another exciting discovery is the presence of organic molecules within HH30's disk. These molecules, including methane and carbon-based compounds, are the building blocks of life. If they survive the chaotic process of planet formation, they could be the spark for life on future planets. This reinforces the idea that the conditions that led to life on Earth may not be unique, but instead could be common across many star systems in the universe. What will the future hold for HH30? Currently, HH30 is still in the very early stages of planetary formation, so it will take millions of years before any planets fully form. However, astronomers will continue to monitor this system to see how it evolves. Future telescopes, like the Extremely Large Telescope, ELT, will provide even more detailed views of forming planets, helping us determine whether HH30's future worlds could support life. The search for life, what's next? The discoveries in HH30 are reshaping our understanding of planetary formation and expanding the possibilities for life elsewhere in the universe. With future telescopes like the ELT and the Nancy Grace Roman Space Telescope, astronomers will be able to study protoplanetary disks in even greater detail. The big questions remain: how long do organic molecules survive in these environments? What determines whether a system forms rocky planets, gas giants, or nothing at all? Could HH30's conditions lead to Earth-like planets, or something completely different? If organic molecules are so common, how many habitable planets might be out there? Final thoughts: HH30 is giving us a front row seat to one of the most exciting cosmic processes, the birth of planets. Webb's discoveries confirm that dust grains are accumulating, planetary building blocks are forming, and the ingredients for life are more widespread than we ever imagined. And this is just the beginning. Every new discovery brings us one step closer to answering one of humanity's most profound questions: are we alone in the universe? If you found this exploration of HH30 fascinating, hit that subscribe button.